Good morning, gentle readers, fellow Earthlings. Today is May 11th, 2025, a wonderful day. And today, from a study with Ross Finlayson, here's Logos 2000, 21st Century Foundations. Foundations of logic, foundations of mathematics, foundations of physics, foundations of science. Foundations is the study of the fundamental theory overall. And the idea is that there is one, and then that there's kind of a candidate for foundations, which is the current sort of premier theory, or that which is considered the ideal theory, or the best theory. That foundations is the theory of everything, and so it's rather grandiose, of course, and it's sort of ambitious to try to figure out what is a foundations. So efforts in foundations over time have largely been matters of reason, and also matters of philosophy. And so in the matters of reason and the rationality for the real and the natural is the idea that there is sort of a one world hypothesis, and there's the idea that the laws of physics are the same everywhere, and that there's is sort of a rule of nature, a natural order of things, although that term is a bit loaded because it's also in the humanistic sort of approaches to things intends to entail what, like Mike makes right, and other matters of politics or the polity of things. But that there's natural order here is a little bit refurbished in the sense that it just means that there is a mathematical order, and then it results somehow that in our complex world as of after life, that being sort of the activity that opposes entropy as diminutive and attenuative and dissipative, that there's a sort of other definition of entropy, which is kind of relating the two various usages of the term entropy with regards to Leibniz and Aristotle, that there's as well that the emergence of higher order constructs, for example, thinking beings up after feeling beings, for example, human beings, that this is thusly sort of a way to accommodate that there's this natural sense of things and a mathematical reality, with as well all the ideas and the ideals of the space of theory, and that which may be contemplated in terms of contemplation and deliberation, those being kinds of the acts of inference and reason, as with regards to then the scientia and intelligence and the wisdom and these kinds of things. But mostly the science and the intelligence, because the wisdom is sort of related to the human condition and the humanistic and this sort of thing. So foundations in the mathematical sense, here is after one of the greatest developers of this is regarded as Augustus de Morgan. And so in the Victorian England, or in about 1850, Augustus de Morgan came up with P's and Q's. These are propositions P and Q that relate to each other in terms of direct causality and the implication, and that thusly when these propositions are variously so or not so, then there's a table of all the different combinations and what results if this then that, if not this and not that, all these kinds of conjunctive and disjunctive results that make for the most simple case for tertium non datar, the excluded middle. There is no third ground, there's only true or false. That for the then given establishment of the derivations of P and Q in terms of each other, that then Augustus de Morgan is who is ascribed as just having given this simple table of things. So it's almost completely sure that being a simple matter of Boolean modal logic, that while it's ascribing a symbolic representation of things, so that it's symbolic logic in the sense, it's algebraic, and it's just kind of a model theory as with regards to what builds for a proof theory of things, that makes a model of abstract Boolean, and in the sense of true or false, that Boolean, the modal, and as also with regards to George Boole's symbolic logic, that the ideas then of from this time, 1850, came to be that was part of the foundations of abstract symbolic logic. So it's always been the case, or at least since antiquity, that the abstract of logic was given from the forms of syllogism as those being derivable as about the causal, what are the relations of implication. So then for entailment and monotonicity, these being extensions of the comprehension of these terms, these simple inductive closed terms, otherwise these proceedings have always been a sort of part of the collected establishment of reason. So sometimes that was matters of rhetoric, and that's kind of how it began to be explained, because it's just mixed for what you might say would be relatable terms, that then fast forward 2,000 years to 1850, and then there's something along the lines of De Morgan's rules and Boole's, because then Boole took this symbolic attachment and they made it for, connect that to arithmetic, an arithmetization of the objects. As after otherwise, according to algebras, any kinds of algebras, magmas or algebras, algebraizations of the objects. And then that furthermore, it arrives at kind of like in the space of these words, it takes these utterly kind of disparate domains, words and the objects of geometry, makes geometrizations of these objects. That then, in terms of model theory, it's simple to have a model of propositions P and Q, or a model of an algebra's objects, or a model of geometry, if there's only one at all, that then they can be related together to make this model theory and proof theory are together. And so when a proof theory shows derivations, reductions, and that which can be possibly made also from building not just the interior reductions, but making the exterior products and then showing how it falls back in. That's another example of the employment of comprehension to make proofs and mathematical proofs. Then there's also that model theory and proof theory are equity interpretable. And so then it results in the theory that there's a model theory, it has that there's this structure of truth that this natural universe, mathematical, that then the idea is then that makes for kind of the grand model theory of everything, or foundations. So then trying to figure out how that can possibly be so almost immediately arrives at the mathematical paradoxes of logic. Just from thinking, well, what about things that are just equal to themselves, or they relate? Or what about things that they don't? And then trying to relate how then in the comprehension is the expansion of comprehension, usually. Meaning it's like, well, if it's so for this and these are as so, then it's so for all these together. What expands the comprehension? Then a restriction of comprehension is kind of taking a narrow view, saying we can only see through this particular lens, and then thusly these are is so not dissimilar that they are considered the same. And so it's about similarity and dissimilarity, and like and unlike, and all these kinds of things that those make for the paradoxes of mathematical logic have that they are to be resolved, to figure out what is blocking the inference, or that there's false or unstated true assumptions that must be in place for there not to be otherwise a contradiction. That the basic measures of quality or existence at all in a model theory where the structure must exist and altogether of any kind of theory at all. Theories don't have to be grand universal foundations. They can be any kind of theory at all. That consistency and completeness are these two major sorts of things that indicate whether a theory is any good at all, because it's not broken. Or even then that we can, there's theories of theories of theories, that you can consider a theory that's broken as an example of showing, for example, simply how this kind of broken theory is a good example of how then the inference about it can establish why it is so, and how to resolve what was broken and then make it whole again. So these are the kinds of ideas that get into the turning over the things and the discovery of things. The consistency and completeness then are for any given particular theory, and then a putative model of this theory, and a candidate model for this theory that's a candidate theory for this sort of truism. It's towards establishing then later in a scientific sort of theory or in a belief system, or to just pick it up and put it down as trying to fit it to any kind of situation, a situational theory or an ad hoc theory. That these all sort of arrive as after that there can't be any mathematical paradoxes or logical paradoxes left in them at all. The usual first sort of logical paradox is the liar paradox. This sentence is not true, it says of itself. Well, so it can't be, and then it says this sentence is not true. A double negative removes itself. This sentence is true, but this sentence is true, it says it's not true. It's a liar. It says something about itself that it's not so. So then this is often connected to something that is in an improbable or impossible situation, like the barber. There's a closed population of all people, everyone who sees the barber, but the barber, there's only one individual, shaves the hair of everyone except who does not shave themselves. Yet it's a matter of comprehension. It's like he must be included as well, he or she, he must be included as well. And then it's just an example of this lower level liar paradox. So what it kind of works up here is that there's an absolute language of perfect mathematical structure. It's called the Comenius language, this sort of universal thing. And it doesn't say much, except it says all the truths in it somehow. And then at the very end, it's got the liar paradox there. But it doesn't result as a paradox because it's just an example of what would be a paradox. So in this way, the paradoxes of mathematical logic kind of start getting chopped right out from under the root. Now this is difficult when the idea and the concept of theory doesn't already have this kind of thing to exist, because there's nothing to hold on to there. And so it's just like whatever comes out as any form of contradiction at all makes everything, according to this notion of the ex falso, out of falsehood, quod libe, anything. Compare this ex falso, out of falsehood nihilum, nothing. That's one of the problems of ex falso quod libe, as a kind of an ultimate effect. When that otherwise, what would happen is you can find somewhere, it's like, obviously I've seen examples of mathematical proofs where something occurred, for example, dividing by 0 is undefined, and that was taken as defined. And then it was shown later that then you could arrive at any kind of arbitrary proposition at all, like 0 equals 1, which is not true. And so I said, well, obviously then we can, out of any kind of broken or inconsistent derivation, then anything can possibly be made so out of it that's just arbitrarily bizarre, even though it contradicts all the other facts. Out of fallacy, anything can be arrived at. But the idea is that then rewinding that and using that example of a broken theory as a model of inference about reason, about repairing or rehabilitating, reforming this theory back into the study of why it is so, then that very act of identifying with that very non-paradoxical example of something that's just merely contradiction in itself, a thing in itself, contradiction in itself, is then able to take out this, not just this inner view, the deductive elimination, but this deductive establishment, and then a deductive elimination to save the course of what was the very narrow course of induction, which is simple, and does then result this kind of shining line of something that's so and a path, that thusly the paradoxes of mathematical logic are kind of eliminated from the bottom, from providing a kind of universal infinite up front, a monism, a monad, as Leibniz might have put it, one, as Plato might have put it, that makes it so that that's already kind of in place, so that this sort of Comenius language is an idea then that there is a universe of propositions that are true, and then we don't know what those are, except that there exists one. And then the idea is that Coleridge language is natural human language of any kind of form, natural language of any kind of form, that's in its intersubjective terms about these objects of logic and mathematics and reason. The object sense for the word sense, time sense, number sense, sense of the continuum, these noumenological senses that then make it so that our phenomenological senses like taste, touch, smell, sight, and hearing aren't boggled, because the only words we can relay are ultimately ungrounded and unfounded. So being able to get rid of mathematical paradox up front, that kind of speaks to some of the talks here, like that paradox-free reason bit. And yet then for the logic and foundations, it's kind of to start from a beginning, and then to arrive at how there cannot be any logical paradoxes. And that there can be the consistency and completeness then of the theory. How can the most simple consistent theory doesn't say anything at all? How can there be a consistent and complete theory, and then it's constant? It's like there's one theory, and that it's concrete, that it's actually always so. The idea is foundations, there is that. And then that gets into the truth of logic, the universe of mathematical objects all together, somehow none contradicting each other, all under sufficient disambiguation, all one consistent and complete world and constant. And then with regards to physics and how that can be concrete, the real theories of physics, or the theories of real physics, and for the mathematical interpretation and the physical interpretation of the mathematical models and physical models, all one sort of model theory, that being theory of everything overall. Of course, there's the ideas then that this universal super scientific, supernatural, is given its own realm of, as with regards to that we can't disprove anything to do with a sort of a higher power, anything outside that anyways. Yet as well we can achieve to receive what can arrive from that as perfection. And so that there is an idea that there is at least one perfection in the universe, not that we have it, not that as finite creatures there's anything that can be utterly yet contained in our deliberations of it, yet that there is one. And so at least then we have a deductive account why our completions that we intend to entail from the theories of limits, or the unbounded and the means of exhaustion, aren't doomed to fail by these inductive impasses existing and being unbridgeable and uncrossable, that these analytical bridges of the deductive results so exists, and that is pretty simple, and that this gives a grounds for there being at least one true reason at all. So here, a modern logician and student of and a researcher in foundations today might say, hey, we're logicists as positivists, and so now there's none of that. It has to be, positivism is only what we can say, so we must axiomatize it, so only what the theory has is what's said it has is in it. Well, so besides that, there's one here, for example, that this is the all or nothing theory that happens to always be constant and concrete in its consistency and completeness, those being this for constancy and diversity and variety, all the different things it can be together, that then it would otherwise be sort of possible to then point that and said, well, in this theory then that is only a tiny fragment, or in its comprehension that's not extraordinary. It's an extension. This gets into things like besides simple things like finger counting, stoplights, and otherwise closed categories, what to do about things like time or like infinite models of the integers, the actually infinite as well. Here there are things like the actual vis-a-vis the potential infinite. We can point at Aristotle and say there's at least a point in Aristotle where he says it is so. And so we have otherwise that being the great authority of all the canon and dogma that so followed. Then we can also point at Kant, for example, with his discussions on reason and judgments of the factual sort or matters of fact, as also as providing the sublime, and besides the Ding an sich, the thing in itself, the sublime, that which is more than itself, it's extraordinary, so that must already exist. And then Hegel gives this great foundation for metaphysics, is this being and nothing, weighing on each other, weighing against each other, dually self-inconsistent, either way the same, resulting this sort of overall concern, making of foundations for our foundations, instead of presuming to stipulate from some axioms like this. So otherwise, a next sort of usual thing is besides the infinitude of integers, an integer continuum then is geometry, and it's like, well, it's after Euclid's geometry because we have Euclid's elements, points, lines, planes, ... and as with regards to them, and it's like that's an axioms that make it so. It's like, well, we can arrive at kind of an axiomist geometry from an infinity of integers, making a linear continuum of real numbers, a continuum. And then as of that being from kind of, well, there's nothing, and then it's not points and lines and planes and ... out into a space, which never really exists. But it's a point in a space, and then it's just the least amount different, and yet achieves all the differences, diversity and variety, that then this spiral space filling curve makes the same sort of model of a linear continuum after an integer continuum, first a unit segment, and then later for these other matters of altogether the continuous domains is kind of considered here, hopefully thoroughly. Then we have the ideas of numbers and objects of geometry, as for a logic being that those at least are logical, and they have a structure, and they're modular, and they're replete in their completeness already. And so that then when we get to something like Euclid's elements vis-a-vis logicist positivism, we can say we have arrived at it in an axiomless sense. Axiomless. That this sort of axiomless natural deduction makes this axiomless geometry, that then it just so happens to make it so that, and of course it's given the light of all the results that follow from something like geometry, Euclid's geometry, to make it so that then at least there's one thing altogether that fulfills that, while already having forestalled to be resolved all the mathematical paradoxes and logical paradoxes, so that anything above that must be somehow so. And if it's found a perceived paradox, instead that's just something wrong. And then when usually in the courses of development of an inductive account, the perceived paradox is used to make a restriction of comprehension instead of expansion of comprehension. This being pretty much the great enterprise of modern mathematics, say, or modern foundations, or the fin de siècle 20th century foundations, blinding one to otherwise this expansion of comprehension, which may so proceed, as we've been discussing, as for example from Quine the other day, and is a pretty usual thing that is like so, has that the logicist positivism then starts being sort of shaky as a weaker logicist positivism. yet that for all what it is and what it entails and what's meant to be for the intersubjective and the formalizable, the formal, that makes a stronger logicist positivism, as from this axiom and this natural deduction from a strong mathematical Platonism, that it exists, and so thusly it can be discovered, and that then it makes for things like the paradoxes of induction, or otherwise that any theory that's given as axioms can be just given counter axioms that contradict it. And then with regards to whether it's science figuring that out, or the empirical, or that there are absolutes, as that this is another thing to reintroduce the idealism for the analytical tradition, because they both need each other to arrive at either one being good. So that's the usual sort of idea here for foundations, and then it result then for something like mathematical universe hypothesis, and then can we figure out the laws of physics from that too? Is the idea that after this linear continuum, then is the folding in and out of that to make three dimensions in the infinitesimals and infinities of an integer continuum, advises among reasons why there are three space dimensions according to all observation and measurement. And then the time is just kind of like the reverse unfolding of that, this silver thread, the continuity again that goes back together. That the resources, these numerical resources of space-time, is the idea, is exactly the same as there exists in one mathematical universe at all. There's only one linear continuum at all, one integer and linear continuum, that then everything else is a stellated yet reticulated and fully rather detailed, the ornate of these things, from this vague fugue, this toccata of otherwise this absolute continuity. This is something that reflects on most matters of fundamental idealism, and also the analytical tradition then so follow, is that our analytical tradition then is something that can be relayed in words, is intersubjective, that we attain to this interobjective in it. So we have words for these things. Arriving at it from there not being any mathematical or logical paradoxes somehow, that then thusly everything is one great grand theory of everything. That's in so few words, must be in this absolutely least amount of words, or none, to arrive at an integer continuum and a linear continuum and a long line continuum, all the relations in one. So that then can help explain then, as we get past just kind of the backdrop of a physical universe, space and time, then all the contents and the state, vis-a-vis state and change, that the idea is sure is that's also framed in terms of the concept called mathematical universe hypothesis. That thusly is just due to the resource of mathematics themselves, that according to these principles of symmetry and conservation, or continuity and reflection in a sense, greater principles kind of surpassing those which are used as the rules and the rulial in our mathematical models, the physical models of physics. That this is one way that there is one way, and to have it that the resources of mathematics make for a mathematical universe hypothesis of physics. Now, it's kind of dangerous to give the idea that there's a mathematical universe hypothesis for physics unless the mathematical universe is all this paradox-free and having it's being thoroughly replete, because otherwise it would just give a half account of what would be the mathematical objects to be physical objects. Yet, while it's so that sometimes you'll hear mathematical universe hypothesis and it's like, we live in a digital world, we might be living in a simulation and all these other kinds of unfalsifiable things, yet according to these ideas about mathematics being finitistic, would would kind of follow, is that is not so. So here the term mathematical universe hypothesis is kind of appropriated, be more of this like a complete mathematical universe hypothesis. That then it's intended to entail that, yes, from the very idea of the mathematical resources existing at all and the great bookkeeping of the cosmic clockworks to make the state and change of all the universe, that is one thing like this. And it's the foundations. And so that way the one theory, in so few words, can be rather contained altogether in this sort of notion, instead of being a billion shards of a broken mirror all falling away and reflecting each other a piece. Well, it can still be that too, in terms of all the theories. Because theory, thought, freedom of imagination and freedom of thought doesn't need to carry any of this kind of stuff. It can be anything, whether it can conceive the inconceivable, it can be paradoxical, it can be fantastical, bizarre, whimsy, all these kinds of things. That's freedom of thought and contingencies. But it needn't necessarily make it so that it's not then just possible to reconsider the truth of the matters and to always have that being an absolute again. So since logicist positivism and scientism and these sorts of schools came to abandon absolute truth and make for model relative truth, or sometimes what's called Tarski truth. Here there's still a real one, and then insofar as it's otherwise in terms of science, something can be said to be true and said to be actually matter of fact and quite true. And so not only does that kind of better reflect common wisdom and the natural meaning of the term and words and language, but it's also allowable because by building the stronger logicist positivism as descriptive and having forestalled and took away what are perceived paradoxes and weaknesses like Derrida and Husserl have about geometry, or what Quine brings up about the modern mathematics and the entire endeavor, that this is considered better and actual. So that may go a long way toward, otherwise the disappointment that almost inevitably arrives at when someone's told that there's not real truth or something like that, that's considered counterfactual. And then it's also helps that some employ logic for a capricious or bad, arbitrarily not good, or asymmetrical or unfair kind of applications, or the art and practice of making lies or something like that, using logic to make a red herring or a straw man or any of these other fallacies of inference and logic, or insufficient knowledge, or otherwise merely talking past each other. Any of these kinds of reasons to reflect on why the logic makes it like so. Has that logic has some its pitfalls, that anything that you can attach to saying that it has a paradox then is suspect as being not resistant to meddling and easily fooled, and Aristotle won't be made a fool. And one avers that Aristotle's fuller reading does not allow people to misuse Aristotle either, these half accounts. So material implication is out. It's called quasi-modal. A real logic is temporal in the sense of being modal, so that entailment and monotonicity are considered actual, and by their definition, and not as of the quasi-modal account, that inductive accounts proceed, and that to have that where they arrive is for a fuller deductive account, not merely the quasi-modal account that's just like first wins C rule 1 and last wins C rule end. Instead, it's like first wins C rule 1 according to deductively the space of that rule. What it rules, the rulial. That the rulial and the regular is the key thing for inductive accounts and their strengths and their blindness. And so they're invincible sort of ignorance. So here it's given that something must be able to say why in the yin-yang ad infinitum that the perimeters of the inner and outer circles are always the same, yet eventually the inner circle is flattened to a straight line. It's different, that in the limit, the infinite limit, is not the same as the case by induction. To make for so why in the objects of mathematics that are real, there are cases for and against infinite induction that are deductive and not inductive. To contrast that with the application of quasi-modal logic, which would just say, oh, well, that's not true today, so we'll just forget it, and leave all this veritable pincushion of tripwires of a minefield, of a hazard, of what's supposed to be the truth tables. So in this manner, it's possible to take some of what are the expediencies afforded by a sort of false restriction of comprehension, instead of resolving it to a paradox-free logic, these ideas of what make regularities and realities and logic, they have to kind of get figured out them together. So in logic today, we have Zermelo-Fraenkel set theory. Our premier theory is called set theory with Zermelo-Fraenkel set theory. What it has expansion and comprehension about a theory of objects with one relation, L, being an element of set. So then we eventually get into paradoxes like class set distinction, or the set of all sets being its own power set. This is after this one regularity. We have three kinds of regularities to consider. And so the first is well-foundedness. It's called regularity. And it's so in Zermelo-Fraenkel set theory, it's like that there are no infinite descending epsilon chains, that it's anything eventually has kind of a base or root. So it's given as that's also sometimes called the axiom of foundation, the axiom of well-foundedness, or the axiom of regularity. So they're all the same thing, and what they say is that the transitive closure of a set is recursively well-founded in this way. So that's one of these kinds of regularities. Then another kind of regularity and ruliality in this Zermelo-Fraenkel set theory is Zermelo-Fraenkel set theory with the axiom of choice. So they add another axiom of kind of an expansion of comprehension. After regularity is the restriction of comprehension, and then the ordinary infinity is a restriction of comprehension. How could that be? Didn't infinity mean expansion of comprehension, saying there's an actual infinite? Well, yeah, except it says there's an actual infinite that's ordinary and regular, which by comprehension it would not be. That infinity is extraordinary, see. So this second regularity, ruliality, added to Zermelo-Fraenkel set theory is called Zermelo-Fraenkel set theory with the axiom of choice. The axiom of choice, that out of any kind of set, there can be established a well-ordering. And what that means is that any well-ordering always has a least element. And so then it also has a next least element, that it has a transitive ordering all the way back out. So this well-ordering is kind of like it's all the way down, and the well-foundedness is all the way down, and the well-ordering is all the way back up. But they're not the same, and they don't necessarily agree, and they're two different regularities. And so in the ordinary, they can be found to break each other. Okay. And so then there's a third kind of idea is kind of be attached as like univalency. It's like, well, we can expand comprehension and take the pairwise union, and then univalency is kind of like, well, we can take this infinite union. So you might call that a regularity of like dispersion, say. It's like we can always spread it out. And so this is that there are at least three kinds of regularities and rulialities that affect each other, because inductively they make great strength rulialities and regularities in the theory like set theory with exactly one relation, L vis-a-vis its complement member for sets versus classes, because then we get in all the matters of comprehension with set theory and foundations, and this is the least amount of baggage. And then that after that, all of modern mathematics has been built in descriptive set theory. First ZF, then later ZFC, because so many results in mathematics can immediately be shown to not arrive until they're given some means of getting the well-ordering principle. So you got well-foundedness, well-ordering, and then this well-dispersed kind of the three things, if you call that univalency or the illative, say. That these then are end up being at odds. But then the simplest form is kind of the Zermelo-Fraenkel set theory by itself. All expansion of comprehension, including an infinity, except it's all closed. That's the axiom given that kind of ends up disqualifying itself because it's a stipulation. And so there's means via induction to show it's wrong. That at least though there's these three realities that later here are related to these three kinds of infinities and three laws of large numbers, three continuous domains, and this sort of tripos making for that it's at least possible then for the deductive results to build the analytical bridges among them, because otherwise it's possible to just say the whole thing is wrong, and to be justified saying that because the inductive results like infinite sets are infinite and these kinds of things. So it can't be closed because it wouldn't be complete. Yet somehow it needs to be consistent and complete. And so then before we get to something like Gödel's incompleteness, because eventually Gödel's incompleteness for any of these finitely axiomatized theories will say, even if it's consistent, the model of arithmetic, then it's incomplete. But not if it's axiomless or universal. That's only from the very act of kind of carrying out and laying over these things. And indeed, then the power set result also has these entirely compelling reasons why, after the otherwise entirely compelling reasons for uncountability, that then we would talk about like the paradoxes of mathematical logic in set theory. So there's Russell's paradox, which kind of set up the whole thing of restriction and comprehension. I call it Russell's reto-thesis, because Mirimanoff, for example, and Skolem will provide that, hey, these models of integers are fragments or extensions. They're not standard because to be infinite, they're extraordinary. So and then that same thing happened to Frege. Frege came up with one of his Grundgesetze of elements. He's like, I've been able to close arithmetic. I made an ordinary closed arithmetic. And so Russell wrote him a letter and said, here, let me show you how to make a paradox out of that. And it's not. Your whole system is broken. And that really put down or submarined, as I put it, Frege's effort in this Foundations of Mathematics. So after De Morgan and Boole, mostly De Morgan, Boole is just kind of out there, but out there. Then there was C.S. Peirce, Charles Sanders Peirce, and the Americans, and so he came up with a lot of stuff about type theory, about small logics that are abstract, symbolic, and formal, and some great stuff to do with types and universals and particulars. So, and of course, all advised by the canon. And I mean, these you can find these same reflections all the way back in any kind of school. And then there was Frege and these sorts, and after like, it reminds me of Newman or something like that, Carl Newman or something. There's lots of logicians, duBois-Reymond about the infinity. And then these higher order super classical bits are like Leibniz, duBois-Reymond, and these Cantor in the late 1800s, as regards to these orders of infinity and matters of infinity. So Russell then came up and said, oh, no, now that we've definitely put that out as a way, well, we'll just make it as so that that later Zermelo and Fraenkel will just say one of their axioms is it's not so. That's the axiom of this ordinary infinity in Zermelo-Fraenkel set theory, is that there is an infinity and it's not so that Russell's paradox applies to it. Now, it's just that entail, for example, that by a most usual construction of numbers and ordinals, you can say that they're just the finite ones that contain themselves and that don't contain themselves, according to make Russell's object, does contain itself. And so it's possible to just build it back again from what was defined away. And the idea is like, well, see rule 1, that's been defined away. And it's like, I'm sorry, but you defined that away. And so now it's back. And so thusly, Russell's reto-thesis is when I say generally, because Bertrand Russell is held up as really just a great in logic. And so when I hold him up as kind of not this paragon of logical virtue, because there's perceived hypocrisy, that's not to put down otherwise his general course of what is good and what can be held up as itself self-consistent, only that in the incomplete, eventually some of what is put up as his truisms are not acceptable. And so I wouldn't, it's not a matter of saying that, well, Russell was wrong, except that the idea of being able to address why Russell was wrong is needed to be included in logic more thoroughly since way back. Now, at least we can point all the way back to something like Chrysippus's moods and the much fuller Aristotelianism to find examples of why this is so, and also over the course of things like when discussing like Occam's nominalism, or Plotinus, or Philo of Megara as having like this half account is built in, that can be kind of put in its little box in terms of this wider world, so that Russell is just kind of a sign of the times, then as regards to logicist positivism. And then similarly for Whitehead, because Russell and Whitehead were given, after Russell wrote this Principles of Philosophy, then this Principia Mathematica, which is supposed to say, and here's how we arrive at a model of 1 + 1 = 2. And that was supposed to be foundations, when it's more of a mere inductive course to arrive at a formalism for finite arithmetic. So then we got the Zermelo-Fraenkel set theory, and then what became descriptive set theory. So then for model theory, which is basically the idea of abstraction and the symbolic at all. So it's not merely like the schools that resulted what we call model theory today, but that is pretty much the matter of abstraction in symbolic relation at all. And so while model theory today is got its language of a model, witnessing, modeling a structure, the very verb itself, to me, the structure of things, matters of structure and logic and reason are up and down the line. So for Tarski being kind of like held up as this great mathematician and logician, after and then kind of with von Neumann and Zermelo-Fraenkel set theory, so kind of this German school, yet with this kind of British influence then to like Quine and this, after like the Vienna Circle and all this, to make for what came into being then called classical logic in the 20th century, is that I really feel that it was unfortunate that the quasi-modal logic is so often included in it, instead of trying to figure out these three regularities and three rulalities of the well-foundedness, well-ordering, and well-dispersed, that it picked one, and then it's got all these things with class set distinction that can be developed in just a very brief model of things, just from alternation itself, instead of carriage, in a sense. So that said, then these are otherwise considered like the great 20th century logic. So this modern logic here, this modern mathematics is including that for this descriptive set theory, a theory of one relation, for the objects of mathematics to so follow, but then that the superclassical things already exist, and the promontories are built on them. And the idea of something like the mathematical inductive limit, and then the infinite limit, and then the continuum limit, are as of these examples that we discovered, and they're not a result of stipulation, which is ultimately unfounded, and is obviously, according to Gödel, for example, incomplete. So after Zermelo-Fraenkel set theory came along, and it's great, it's like, well, we've rewrapped Frege's pretty much as Zermelo-Fraenkel set theory, so we got a list of axioms, and then everything else follows from that. And then there was Gödel, and he kind of came along and says, well, look, now I've made a model of arithmetic complete after something like Giuseppe Peano and a bunch of other actors in the late 19th century who, after Emile de Bois-Reymond and these other kind of thinkers in the infinitary reasoning, that they were kind of like appropriated and said, well, now we're using these models of ordinals, integers. And John von Neumann is like, well, I'll make more models of integers in this way and that way and bring them on around and these kinds of things. Like Gödel arrived as like, hey, I just kind of like the idea of the stroke is like you can take Russell's reto-thesis and apply it to finite numbers and those as sets and show that it's Russell's paradox again, if it's ordinary. Then Gödel took the models of arithmetic and everything was doing built arithmetic and he applied diagonalization to that again, and he showed that was broken open. So it'd have to be inconsistent if it was complete and incomplete if it was consistent. Gödel's inconsistency. So, and then he proves things like, well, I'll prove the independence of part of the continuum hypothesis, and then the later so that just shows that it's open from its own application. Then later Cohen came along and he says, hey, we wouldn't want it to be inconsistent or incomplete either way to have the continuum hypothesis. So I'll show that it's independent of the axioms of ZF because how did he do this? Well, I've implemented this technique called model forcing, which makes it so that at the end of having an inductive account, the rulial and the regular, I'll take the model that was inside and make that one outside, and then take the one that's outside and make that one inside. So it's extraordinary to be this way. He basically added an axiom at the very, very end of his proof to make it so, and so nobody would really know that unless they read the whole thing. But if they didn't otherwise, then anybody could pick up the fact that Gödel was about halfway out, but he couldn't get back in, and show that the whole thing was just wrong. The X follows quadlibet. Now it's inconsistent altogether. So anyways, it's not inconsistent. It is incomplete though. And then to make it complete shows that as this blind, half-blinded, half-account, half invincibly ignorant, invincible, and half-blind because of the restriction of comprehension, then instead it arrives at something that's this fuller, replete, superclassical, extraordinary from this paradox-free foundations here with inverse contradiction not in itself, that these are the kinds of things that they can arrive at kind of reformulation of that. So that's what I've been thinking about since studying this for a while. And then I've been reading this DesCartes, A Discourse on Method, this word and object from Willem van Orman Quine we were looking at the other day. And here's something we are going to look at today. This is Russell and Whitehead's Principia Mathematica, the first section, or to number 56. So it's published by Cambridge at the University Press. He says, in making deductions from our premises, we have considered it essential to carry them up to the point where we have proved as much as is true in whatever would ordinarily be taken for granted. But we have not thought it desirable to limit ourselves too strictly to this task. He talks about particular cases, cardinal arithmetic, finite numbers. But its general laws hold equally for infinite numbers, ordinary infinite numbers. There are others. We have found it necessary to give very full proofs, which is fair. It's to be didactic. logic of relations, primitives. Dr. Leon Twistek took the heroic course of dispensing with the axiom without adopting any substitute. From his work, it is clear that this course compels us to sacrifice a great deal of ordinary mathematics. So, referring to Wittgenstein and Dedekind and Cantor, that Russell's paradox is that the set that doesn't contain itself would contain itself. And then there's Cantor's paradox is that, well, the set that is his power set is equal to itself. Like the universe would be its own power set. It's already includes all these things again. It's extraordinary. Yet, in the ordinary, that would be a contradiction. So in this universe of the sets, there is no class of all sets, no set of all sets. And so that's it. For other types of theories that are anti-foundational in the sense that there are, of course, many other efforts to study theories that, well, we don't have this regularity axiom, we have this other rulial axioms that establish their regularities, their rulialities. So, with universes in them. So the idea is like, well, there is one that does. So then there's Burali-Forti's paradoxes for the ordinals. It's like an ordinal, when you consider it as like all the lesser ordinals by this ordering property with regularity together, would include itself. It would be an ordinal to collect and consider these Geshamo, these ordinals. Burali-Forti's paradox. So Russell's paradox, Cantor's paradox, and Burali-Forti's paradox. Myhill, these are kind of like given as the usual paradoxes of ordinary regular theory, because there's more extraordinary yet regular theories. And in Russell, it says, perhaps some further axiom, less objectionable than the axiom of reducibility, might give these results, but we have not succeeded in finding such an axiom. Well, it needs an entire course about the inductive impasses in analytical bridges to put these regularities together. Because otherwise, when you add these axioms like choice and well ordering and well-foundedness together, they can result breaking each other. Well-dispersive, well-foundedness, and well-ordering together, they can result breaking each other. So the theory is kind of stuck in terms of then all the rest of this axiomatic set theory have been being built on it. And descriptive set theory and model theory for up to analysis after delta epsilonics, that being the course, and for measure theory, that being mathematics today, has that there's not really an axiom you can add. It has to kind of result being figured out what the regularities and rulialities are that come into it from this geometrical universe. Why it is so. And that is part of the thing in foundations that is part of the enterprise. That it results trying to add something isn't going to work until it's kind of put together back how they can be composed and separated, and they do so without breaking each other. So that's the thing. He's talking about Sheffer. Now Sheffer's got this great Sheffer strokes. Sheffer strokes he's just got a good logic. So that's like with Sheffer and Gentzen and all that, I would pick Sheffer first. We recommend this task to Dr. Sheffer, since what has so far been published by him is scarcely sufficient to enable others to undertake the necessary reconstruction. Really? He went on. He talks about atomic and molecular propositions, and then we can get into the whole like particle wave duality bit and wave resonance duality. Preliminary explanations. So I'm to read this again, because when I first look at it, it was rather too dense. And then in this symbolic formulary, inscrutable. And so then to look through this again, this is after something like a Phrygian Begriffsschrift, a concept script. And it's just got a derivation or a logic to say, to write proofs. And as regards to all these different derivations, and there's symbolic logic, Propositions of the above type might be continued indefinitely, but as they are proved on a uniform plan, it is unnecessary to go beyond the fundamental cases of P or Q, not P, P over Q, and P dot Q. So that's material implication for you. And so on. Classes and relations, the general theory of classes. So after he's got through all his kind of proofs, then he's getting to the general theory of classes, because then he'd prefer probably to be able to frame things in terms of that, in terms of the results of the models instead of what has built them so laboriously. So then whether he gets into class set distinction and these kinds of things, I'd be happy to see. Hence, though the above proposition is true whenever it is significant, it is not true whenever its hypothesis is significant. Well, from the above propositions, it appears that although expressions such as this have no meaning in isolation, yet those of their formal properties with which we have been hitherto concerned are the same as corresponding properties of symbols which have a meaning in isolation. Hence, nothing in the apparatus hitherto introduced requires us to determine whether a given symbol stands for a class or not, unless a symbol occurs in a way in which only a class can occur significantly. So significantly means consistently, and it's sort of run out. So anyways, this is considered like mathematical foundations. How does 1 + 1 = 2? Supps's axiomatic set theory, and this is something to get into later time. You know, principles of mathematics. This is Russell's The Principles of Mathematics, so I'll be reading this here for a while. And he gets up in a transfinite cardinal space, the projective theory of matrices, all quite linear and normal things. Here's matter in motion. I'll be reading this some more. From Bertrand Russell, a great logician. You know, the Introduction to the Foundation of Mathematics, or Wilder. This is pretty good. These are just kind of usual courses in books. Schoenfeld's mathematical logic. Better. Schoenfeld's is kind of cool. And compared to something like, and it's not really like the whole world like Moschavakis and descriptive set theory or Jech and set theory, but those are pretty great and getting into things. This is Smolian's first order logic and Tarski's introduction to logic. Then there's some quite fuller and thicker works here with regards to Tarskian logic. And that those are kind of the books that I was going to look to get into a little bit here today. And so then as with regards to so what's considered, it's that there is a foundations. It's extraordinary. It's rulial. It's perfect. To be discovered. It's free of paradoxes. Ain't no lie. And it's includes modern mathematics as an example. Hey, have a great day. Have a wonderful day. So long.